Hello everyone, today we're looking at the Applied Book 2, Exercise 5, Example 10 from the Mechanics chapter of Forces and Friction. And we're going to look at how to tackle this example and then apply it to another couple of questions as well when we're dealing with particles in equilibrium. So in the first scenario over here, I have, or from the example, we've got a 2 kilogram block which is sliding down a slope with acceleration equal to 1 meter per second squared. I've got my weight labeled and my reaction force labeled. Now, because we know it's a rough surface, there has to be friction, and friction will always oppose the direction of motion. So friction in this case is acting up the slope because we're accelerating downwards, we're moving down the slope. Now, whenever we have a question regarding an inclined plane, we have to resolve our forces parallel and perpendicular to the slope. R is a force that's already perpendicular, so it does not need resolving. Friction is a force that's acting parallel to the slope, so it does not need resolving. So the force that does need resolving is our weight. So for this, we always drop a perpendicular and bring it parallel to the other side. So we see this force is going downwards, so this needs to be an arrow down in this direction and an arrow down in this direction to follow that direction. And the 30 degrees comes into here. Now, while we do this, we have now got our forces. We need to now label the perpendicular and parallel component. Well, this force is adjacent to the angle, so this is 2g cos 30, and this over here is 2g sine 30. Now, because this object is already accelerating, it means the frictional force is at its maximum value. So this is equal to mu times by r. So for this question, we are trying to find out the value of mu, and from that, we're going to need to use F equals ma. However, my advice is always to work out the reaction force first, because the reaction force is also linked to friction. And to do that, we can resolve our forces in a perpendicular direction. Because this is only acting in this direction, these forces must be balanced. So if we resolve perpendicularly, we can say the forces going in that direction equal the forces going in that direction. And we can say, therefore, that R is equal to 2g cos 30. Now, because we said this is accelerating, we can also say, therefore, that friction is equal to mu times by the value of R, or mu times by 2g cos 30. And that is important because when we now want to work out the value of friction, we need to look at the forces acting in this direction, and we can do that via using F equals ma. So if we say F equals ma parallel to the slope and down the slope as positive, because it's moving in this direction, 2g sine 30 minus friction is equal to 2 times by 1, and therefore 2g sine 30 minus mu 2g cos 30 is equal to 2 times 1, which is equal to 2. Now, if we rearrange this, we can get the value of mu on its own by bringing it to the right hand side and making it positive. So this is equal to mu 2g cos 30, and on the left hand side we get 2g sine 30 minus 2. And our last step here is simply to calculate what this is and then divide by 2g cos 30. So 2 times 9.8 sine 30 minus 2 divided by 2 times by 9.8 cos 30, and that gives us a value of 0.4595. So mu is equal to 0.4595 or 0.460. And that's effectively what we've done there. It's just worked out the value of mu via resolving perpendicularly and looking at F equals ma parallel to the slope. Now, I said I wanted to build on this and look at friction in a little bit more detail on an inclined plane. And I have this time a scenario which is in equilibrium. And with regard to this question, it's really about understanding what the question's asking. What we have over here is a 3 kilogram block that has a force P pushing it up the slope or acting in a direction parallel to the slope. And it says find P if the block is on the point of moving up the slope and also in a separate part on the point of slipping down the slope. Now, the key phrase in this question is the phrase on the point. On the point of means you are just about to move, and that refers to the concept of limiting equilibrium. So in pink, I'm going to write here limiting equilibrium. And we know that when we're in limiting equilibrium, F max is equal to mu r. So friction in this case will be equal to mu r. So when we look at these two scenarios effectively, if you are on the point of moving up the slope, it means that you are just about to push this block upwards, but friction is what is keeping you back or holding you back. So when we annotate this diagram, we need to get all our forces in first. So we know the reaction force acts perpendicularly, and we know the weight acts downwards in a vertical direction. But the friction in this case has to be acting down the slope for part A, because it's friction that is stopping this from moving up the slope. And for this now, we need to again make sure we resolve our forces correctly so that we can then work out our calculations correctly. So if we resolve our force into the components, we have over here 3g cos 30 and over here 3g sine 30. And I'm just going to do these two scenarios or these two examples on the left hand side. I'm going to do scenario A in green and scenario B in orange. So we said if you are trying to work out the value of P, we need to apply this. We need to first work out the value of R by looking perpendicular to the slope. So we can say R we can obtain by resolving perpendicularly. This direction is equal to this direction. So R is equal to 3g cos 30. Now, because this scenario is in equilibrium, it means the acceleration is going to be equal to 0. So if we apply F equals ma up the slope and in the parallel direction, we can say that P minus 3g sine 30 minus friction is equal to 3 times by 0, or just 0, which means that P is equal to 3g sine 30 plus the value of mu times by r, 3g cos 30. Because in this case friction is equal to mu r because we are in limiting equilibrium. So if we now simply substitute our values in where mu is equal to 0.3, we get a value of P being 3 times by 9.8 sine 30 plus 0.3 times 3 times by 9.8 cos 30, and that gives us a value of P equal to 22.3 newtons. So P is equal to 22.3 newtons. If we now, however, look at the second scenario, this one catches more people out. It's saying that P is being applied and the block is on the point of slipping down the plane. That means the block is just about to slip down. That means I don't have enough force to push this up, and I'm just about keeping it up with my arms. That means the frictional force must be helping to keep this up. Friction always, we said always opposes the direction of motion. In this case, it's about to slip down. Friction is now acting upwards. Therefore, if we now work out the value of friction, or P for this case, we need to now do F equals ma again, parallel up the slope. We know that R is still equal to 3g cos 30. So now we're looking at part B in pink. R is equal to 3g cos 30 again. And what we can say is that when we do F equals ma up the slope, we can see the friction has actually changed direction. So now our equation is going to be P plus friction minus 3g sine 30 is equal to 3 times by 0. And from that, when we rearrange and make P the subject, P is equal to 3g sine 30 minus the value of friction is equal to, minus the value of friction. So very simply, P is now equal to 3g sine 30 minus mu brackets 3g cos 30, or 0.3 cos 30. And now if we work that out, we get a value equal to 7.06 newtons. So P is equal to 7.06 newtons. We see a P is substantially less than the value here, because P here is being helped by friction, whereas here P has to overcome friction. Now, I hope that's made sense. If it hasn't, please comment below or let me know privately. Have a good day. Take care.